In this video, we're going to look at part 1 of the photoelectric effect, and we'll explain what that is and why it's important. A bit of history to start us off. At the start of the 20th century, light was very well understood. James Clerk Maxwell had written a set of complex equations which described light in terms of electric and magnetic fields, which is what we've taught so far in this topic. His work was then vindicated when radio waves were discovered by Heinrich Hertz. There was only one problem: the photoelectric effect. In 1905, Albert Einstein published a paper that explained the photoelectric effect, and in 1921 he was awarded the Nobel Prize in Physics for his services to theoretical physics, and in particular his explanation of the photoelectric effect. The figure below, this image here, shows the emission of electrons when a material is illuminated by light of a sufficiently high frequency. And this ultimately is what the photoelectric effect is. So we have a light that's high enough frequency, electrons are spit out, and that is the photoelectric effect. But it's a little bit more complex than that, and why it happens is not as simple as just saying, it does. In this representation here, we can see that the photon is stripping the electron from the shell, and it produces a product that we then call the photoelectron. So how does a wave do something like this, though? That was one of the problems. There is no way to describe how a wavefront could come in and strip an electron out of its orbital shell and produce a photoelectron. So the experiment that they made to test this used a photoelectric cell, and this was the thing that ultimately observes the photoelectric effect. It consists of a curved metal cathode, which is the emitter, and an anode, which is the detector, in an evacuated glass tube or jar. In order to detect these electrons that are being ejected, we needed the cell to be placed in some sort of a circuit. Because remember, electricity is just electrons flowing. So if we're stripping electrons that are being ejected, we could collect them on some sort of a sensor, and then if we join that to a circuit with an ammeter in it, we should be able to see a current being produced through a circuit. So in order to do this photoelectric effect at a very effective level, or to produce a large number of electrons, we found that very high frequency ultraviolet light was one of the best sources. Because remember, we talked about we need the high energy, therefore we need a high frequency. So ultraviolet was one of the best to use for this. So what did we observe? We've started with our apparatus. So we've got the light coming in, it hits this cathode, this emitter, and electrons are stripped off and fired or launched into this anode, which is the collector. Notice that the curve acts kind of like a lens. If we have light bouncing in and it strips stuff off, it's going to be fired towards that anode. If we just had a flat plate, they would scatter in all directions, but because of the curved surface, it focuses them to the collector. So then we have electrons hitting the collector. If we have enough of them doing that, they're going to flow through the circuit to try and balance out the charge, and therefore we have a flow of current, and we're going to measure a current on the ammeter. So we can see that if we set up the apparatus with no light source on it, we have no current. But as soon as we have this electromagnetic radiation, or this high frequency UV hitting the collector or the emitter, then we suddenly produce this current. So the electrons are flowing in this direction, and then we say that the conventional current is flowing in that direction. So remember, we've talked about that a little bit earlier about conventional versus electron flow, that electrons are actually flowing towards the positive terminal, but that creates that phenomena where it appears like we've got a positive to negative current flow. So when we talk about conventional current, we always say it's flowing from positive to negative, but the electrons themselves are actually moving in the other direction. When light strikes the metal surface, which is that cathode, it ejects the electrons. The evacuated glass tube allows the electrons to travel freely to the positive anode, because if we have air particles and stuff in there, we've got other gases and molecules and things that are going to stop, interfere with, or absorb those electrons. So that's why we need it to be evacuated. So there's nothing to stop those electrons from moving. They move towards the positive anode. They don't hit any air particles because it's an evacuated container, and a very sensitive ammeter records the size of that current. This current is proportional to the number of electrons reaching the anode. If the current, which measures the rate of flow basically, if that increases, then that suggests that you've got more electrons flowing, and therefore they're proportional. So in summary, when light of sufficiently high energy is incident on matter, it can give the electrons enough energy to leave that material, to actually leave their electron shells and produce or leave their structure as that photoelectron. This, if we collect it in this collecting system or the sensor at this point here, if this happens, then we create a circuit, it induces a current, and we've got an electrical current flowing basically from an electromagnetic light source. This is the photoelectric effect. So this whole concept of electromagnetic radiation hitting a surface, it ejects electrons, those electrons then flow through a circuit and produce a current. That is the concept of the photoelectric effect. There are some really important properties of the photoelectric effect, and these are the bits that you really need to know for that SACE understanding concept. And we'll link that into part 2, and we'll elaborate a little bit further. But firstly, electrons are emitted instantaneously. So as soon as the first photon strikes the surface of the metal, regardless of the light intensity, an electron is instantaneously produced or emitted. And it's important to note that it says regardless of light intensity. Number 2, there is a minimum frequency, which we call F0, which if we go below that, no electrons are ejected. This frequency is called the threshold frequency, and that varies depending on the type of material that we use. So in this image here, you can see that the violet and the green both emit electrons, but as soon as we go to red, which is lower down, it's a lower frequency, lower energy, suddenly no electrons are emitted. So red light has the smallest frequency and does not eject electrons. Green and blue, higher frequency, do eject electrons. And you can see a similar representation here, but they've given you the actual frequencies just in nanometers. So it's important, F0 is the minimum frequency, and that's the threshold frequency. That's the point at which we start ejecting electrons, or the lowest frequency that we can go and still produce electrons. Number 3, the intensity of the light affects the number of electrons emitted, not the energy of the electrons emitted. These two factors are proportional. A larger current is detected if the intensity of light is increased, and what we mean by that is that bright light produces more electrons, not higher energy electrons. So if we think about that, it's kind of like bright light is not higher energy light, so to speak. It's just more of those photons to produce it. So more photons strips more electrons. We end up with a lot more electrons ejected, not a few electrons ejected at very high speed, because those photons aren't moving any faster or with any higher energy than any other photon there, just because we increase intensity. Intensity is number of photons, not energy of photons. So that's why they translate. So number 3, intensity of light affects number, not energy of the ejected electrons. Number 4, the electrons emitted have a range of kinetic energies. This ranges from 0 to a maximum value. So it's not just all electrons are ejected at one specific kinetic energy, there is a range of kinetic energies. You can see this below. The violet light has the larger frequency and the electrons are emitted with a greater kinetic energy. So they're leaving here with a 6.22 times 10 to the 5 meters per second, versus the green, which is only 2.96 times 10 to the 5. So that's important. Range of kinetic energies, larger frequency emits a greater kinetic energy. So the intensity of light does not affect the kinetic energy of the emitted particles, but the frequency does. So that's the crossover there. So from here, continue on to the next video if you want. There are no questions for this topic, just because we need a little bit more information and we haven't actually covered any formula, so to speak, yet. We've just explained what the photoelectric effect is, and it's important that you can explain that in your own words. And we've outlined those primary rules or those requirements or situations that happen within the photoelectric effect. So there's things about the intensity versus the frequency of the light, about the threshold frequency, and the kinetic energy ranges. So it's really important that you understand those, and we'll continue this in the next part for the photoelectric effect video.